Listen to the sound of space itself ringing. That brief chirp was the first gravitational wave ever heard, a ripple in the fabric of reality from a collision over 1 billion years ago. These are not mere waves in water or sound in air. Gravitational waves are distortions in spacetime itself, generated by the most violent events the cosmos can muster. Today, we are going on a journey through 25 incredible facts about the universe's most extreme gravitational waves. You will discover how they reveal the origin of gold, create homeless black holes, and might even carry whispers from the moment of creation. What does it mean to finally hear the symphony of a violent, hidden universe? That historic chirp was the sound of two monsters merging. On September 14, 2015, a ripple in spacetime washed over Earth. It had traveled for 1.3 billion years, a faint echo from an event of almost unimaginable violence. This was GW 150914, the first direct detection of a gravitational wave. The Laser Interferometer Gravitational Wave Observatory, or LIGO, had finally heard the universe. The signal told a precise story. It was a death spiral. Two black holes, one about 29 times the mass of our Sun and the other 36, had been orbiting each other in a final, frantic dance. As they drew closer, their immense gravity pulled space and time around them like a whirlpool. The pitch of the gravitational wave rose, a rapid upward sweep captured in data as that iconic chirp. Then, in a fraction of a second, they collided and became one. The energy released in that instant is almost beyond comprehension. An amount of mass equivalent to 3 entire suns was not just blown apart, but completely converted into pure, rippling gravitational energy. For a brief moment, that single collision outshone every star in the observable universe combined. This was the triumphant confirmation of a prediction made a century earlier by Albert Einstein, who theorized these waves but thought they might be too faint to ever detect. That single chirp did more than prove him right. It opened a window onto a dark and violent cosmos we had been deaf to for all of human history. But that first detection was just a single note in a vast cosmic symphony. A little less than 2 years later, the universe performed a full orchestra piece. In August 2017, gravitational wave observatories heard a new signal, one that lasted for nearly 100 seconds. This was not the brief, deep chirp of black holes. It was the longer, rising song of two neutron stars, the incredibly dense cores of dead stars spiraling together. This event was named GW 170817. For the first time, we did not just hear the universe, we saw it too. Just 1.7 seconds after the gravitational wave signal ended, space telescopes detected a powerful flash of gamma rays coming from the same patch of sky. That was the trigger. Astronomers around the world swiveled their telescopes, from radio dishes to the iconic Hubble Space Telescope, all pointing toward a faint galaxy 130 million light-years away. What they witnessed was the birth of multi-messenger astronomy. We had the gravitational waves telling us the story of the massive objects merging, and we had the entire spectrum of light, from gamma rays to visible light to radio waves, showing us the fiery aftermath. That aftermath was something called a kilonova. As the two neutron stars collided and shattered, they blasted out a cloud of material rich with neutrons. In this extreme cosmic forge, atoms were bombarded, rapidly capturing neutrons and building themselves into the heaviest elements in the periodic table. This single event created an amount of gold and platinum equal to several times the mass of our entire planet. It was a direct, spectacular confirmation. The gold in your jewelry, the platinum in a catalytic converter, these are not forged in the hearts of stars like iron or carbon. They are born in the catastrophic, universe-shaking collisions of dead stars, their creation announced by ripples in spacetime and a brilliant flash of light. With that one event, astronomy graduated from watching the silent movie of the cosmos to experiencing it in full, immersive surround sound. The kilonova's light show revealed a universe we could finally listen to. But what are we actually hearing when a gravitational wave passes by? For the faintest signals, the effect is almost impossibly tiny. The first detection from those stellar mass black holes stretched and squeezed the entire 4-kilometer arms of the LIGO detector by an amount 1,000 times smaller than the width of a single proton. It is the most precise measurement humanity has ever made, yet this is just the quiet background hum of the cosmic orchestra. The most extreme gravitational waves operate on an entirely different scale. Fact 3. Some waves are so powerful they warp spacetime itself. Think of the difference between a ripple on a calm pond and a towering tsunami wave in a stormy ocean. The ripple gently lifts and lowers the water's surface. The tsunami, however, doesn't just move the water, it churns the entire seascape, dragging the seafloor, uprooting everything in its path. The gravitational waves from merging supermassive black holes, the billion solar mass giants that lurk in the hearts of galaxies, are the tsunamis of space-time. Their amplitude, their sheer strength, is so colossal they don't just slightly stretch and squeeze the fabric of reality. They twist it, distort it in a measurable, chaotic dance. If one of these waves passed through our solar system, it wouldn't just minutely change the distance between Earth and the Sun. It could temporarily alter the very geometry of planetary orbits, bending the paths that planets follow in a way that would be detectable across light years. This isn't a gentle stretching of a rubber sheet, it's the sheet itself being violently knotted and then released. These extreme waves carry so much energy that they permanently change the shape of the universe in their wake, leaving behind a memory of their passage etched into the cosmic background. We are only just beginning to tune our instruments to hear these deepest, most resonant notes in the dark. These space-time tsunamis are not isolated events. Our universe is filled with a constant, underlying murmur. Fact 4. The cosmos itself is humming with a gravitational wave background. Picture the static on an old television set, that faint, persistent crackle of white noise filling a quiet room. That static is the leftover radiation from the Big Bang, the cosmic microwave background, which we see as light. But there is another, deeper kind of static we are just learning to hear, one made not of light but of gravity. This is the gravitational wave background, a low-frequency hum that permeates all of space. It is not a single chirp or crash, but the combined rumble of countless catastrophic events happening across the universe over all of cosmic time. The primary source of this hum is thought to be the mergers of supermassive black hole binaries. Nearly every large galaxy, including our own Milky Way, has one of these monstrous objects at its center. When galaxies collide and merge over billions of years, their central black holes eventually sink to the new core and begin a slow gravitational dance. Millions of these pairs are likely swirling throughout the universe, each one churning out gravitational waves as they spiral inward. Individually, their signals are too faint and too low in pitch for our current detectors like LIGO to hear. But together, they create a continuous, universe-wide drone, a symphony of the cosmos's most massive objects. To tune into this background hum, scientists are not using laser beams in tunnels on Earth. They are using the galaxy itself as a detector by watching the clocks of the universe pulsars. These are rapidly spinning neutron stars that beam out radio waves with the precision of a cosmic lighthouse. By monitoring an array of these pulsars across the Milky Way for decades, astronomers can look for tiny, correlated distortions in the timing of their pulses. A passing gravitational wave background would stretch and squeeze the space between us and the pulsars, ever so slightly speeding up or slowing down the arrival of their ticks. It is an experiment of almost unimaginable patience and precision, listening for a whisper in the wind of interstellar space. Hearing this hum would confirm a fundamental prediction about how galaxies grow and merge, revealing a hidden layer of cosmic history written not in light, but in the steady vibration of spacetime itself. That cosmic hum is the collective echo of countless mergers, but each individual collision has its own violent story to tell. Sometimes the final act of that story sends its main character flying into the void. When two black holes finally become one, the newborn object does not always settle quietly into the center of its galaxy. It can be launched into exile. This is the phenomenon of the recoil kick, and it creates the universe's ultimate runaway objects. The physics behind it is a direct result of how gravitational waves carry away not just energy but also momentum. Think of a garden sprinkler. As water jets out in specific directions, the sprinkler itself recoils, spinning or even skittering backwards. A merging black hole binary is like a cosmic sprinkler, but instead of water, it is spraying out unimaginable power in the form of gravitational waves. If the waves are emitted perfectly symmetrically, the kick is minimal, but nature is rarely so tidy. If the two black holes have different masses, or if their individual spins are misaligned, the gravitational radiation bursts out more powerfully in one specific direction. To conserve momentum, the newly formed supermassive black hole recoils violently in the opposite direction. The numbers are staggering. These kicks can reach speeds of over 5 million kilometers per hour. At that velocity, the black hole is moving faster than the escape velocity of even the largest galaxies. It is literally kicked out of its home, becoming a rogue, homeless black hole destined to wander the empty darkness between galaxies for eternity. Astronomers have not yet directly observed one of these recoiling black holes in the act, but the mathematics is clear and the hunt is on. We must now imagine the silent, dark expanses between the glittering islands of galaxies. Drifting through that profound emptiness are these invisible exiles, the remnants of the most violent marriages in the cosmos, their birth screams of gravitational waves having propelled them into an endless solitary journey. A homeless black hole is a silent traveler, but its birth cry moved at the ultimate speed limit. Gravitational waves do not just travel fast, they travel at the speed of light itself. This is not merely a high velocity, it is a fundamental property of spacetime itself. When a massive event like a black hole merger distorts the fabric of reality, that distortion propagates outward as a wave at exactly 299,792 kilometers per second. Nothing in the universe can outrun it, but the true magic of this speed is not just in its raw number, it is in what it does not do. Unlike every other signal we have ever used to study the cosmos, gravitational waves are almost perfectly unimpeded by the universe. Light, our traditional window on the cosmos, is easily blocked. The brilliant core of our own Milky Way is hidden behind thick curtains of interstellar dust. The nurseries where stars are born are often cloaked in dark, cold gas. Even the earliest, most precious light from the infant universe had to fight its way through a hot, opaque plasma for hundreds of thousands of years before space became transparent. Gravitational waves face no such obstacles. They pass through planets, stars, nebulae, and entire galaxies as if they were not even there. A gravitational wave generated in the chaotic, dust-shrouded heart of a colliding galaxy will arrive at our detectors billions of years later with its information perfectly intact, carrying a pristine, unaltered record of the event. This makes them the ultimate cosmic messengers. They allow us to peer directly into places that have always been hidden, like the violent mergers of supermassive black holes buried in galactic cores, or perhaps even the very moment of the Big Bang itself, an epoch so dense and hot that not even a single photon of light could escape. With gravitational waves, we are no longer astronomers peering through a dirty, stained glass window at the universe. We have suddenly been given a direct telephone line to its most violent and secret chambers, a line that rings with the pure, undistorted truth of spacetime itself. This direct telephone line demands a receiver of almost impossible sensitivity. To catch the faintest whisper of a gravitational wave, scientists had to build instruments that measure the unimaginably small. Fact 7. Detecting them requires measuring changes smaller than an atom. The Laser Interferometer Gravitational Wave Observatory, or LIGO, is essentially a giant ruler, but one designed to measure distortions in the ruler itself. At its heart are two 4-kilometer-long arms arranged in a giant L shape. A laser beam is split, with one half sent down each arm, bouncing off mirrors at the end and returning to recombine. Under normal conditions, when space is calm, the two light waves return perfectly aligned and cancel each other out, producing darkness at a sensor. But when a gravitational wave passes through, it does something extraordinary. It stretches space in one direction and squeezes it in the perpendicular direction. This means one of LIGO arms gets infinitesimally longer, while the other gets infinitesimally shorter. That tiny difference changes the distance the laser light travels just by a fraction of a wavelength. The returning light waves are now slightly out of sync. They no longer cancel out perfectly, and a flicker of light appears at the sensor. That flicker is the signal. The scale of this measurement is what defies belief. For the first detection, the change in length of those 4-kilometer arms was about 1/1000th of the width of a proton. To put that in human terms, it is the equivalent of measuring the distance from our Sun to the nearest star, Alpha Centauri, over 4 light-years away, with an accuracy equal to the width of a single human hair. Every potential source of noise, from distant ocean waves to the random jitter of atoms in the mirrors themselves, had to be identified and silenced. The mirrors are suspended by the world's most sophisticated pendulum systems, isolated from the trembling of the Earth. They operate in a near-perfect vacuum, one of the largest and cleanest ever created. This is not just astronomy, it is the pinnacle of precision engineering, a silent temple built to listen for the faintest sigh of the universe. And it works because when spacetime itself rings, even a change smaller than a subatomic particle can shout a story across a billion light-years. The mirrors of LIGO are stilled by the faintest tremor of the Earth, but they are deaf to the deepest voices in the cosmos. To hear the lowest notes of the gravitational wave symphony, we must leave our planet behind entirely. This brings us to fact 8. The waves from supermassive black hole binaries have periods that last for years. We are no longer talking about the brief, high-pitched chirp of a stellar collision. We are tuning into the slow, resonant bass notes of the universe's most massive couples. Picture two black holes, each one containing the mass of millions or even billions of suns, locked in a mutual orbit at the heart of a merged galaxy. Their dance is not a frantic, final spiral, but a stately, cosmic waltz that can last for millions of years before they finally coalesce. The gravitational waves they produce are correspondingly immense and slow. A single cycle, one complete stretch and squeeze of spacetime, can take years or even decades to complete. The wavelength of these waves is not measured in kilometers but in light-years. Our ground-based detectors, with their 4-kilometer arms, are simply too small to sense such a vast, leisurely undulation. It would be like trying to measure the gentle slope of an entire continent with a ruler the size of your hand. To catch these waves, we must build a detector of matching scale, one that spans not kilometers but millions of kilometers. This is the promise of the Laser Interferometer Space Antenna, or LISA, a future mission that will consist of 3 spacecraft flying in a perfect triangle, trailing behind Earth in its orbit around the Sun. With arms 2.5 million kilometers long, connected by laser beams, LISA will be tuned to the low-frequency hum of the supermassive black hole universe. Listening to these waves will be like hearing the turning of galactic gears. Each binary system will have its own distinct tone, a steady thrum that rises in pitch as the black holes inch closer over millennia. By cataloging these cosmic heartbeats, we will map the hidden population of these monstrous binaries, understanding how galaxies merge and grow through cosmic time. It is a patient form of astronomy, one where a single data point may represent a full year of observation, slowly revealing the grand, slow-motion choreography that shapes the largest structures in existence. Lisa will listen for the slow bass notes of supermassive black holes, but the early universe might have produced a sound more like a sharp cosmic crackle. Fact 9. Cosmic strings could create sharp, crackling gravitational waves. This idea ventures from the known violence of black holes into the realm of the profoundly theoretical, yet it offers perhaps the most direct window into the universe's very first moments. Cosmic strings are not strings in any familiar sense. They are hypothetical one-dimensional defects in the fabric of spacetime itself, thought to have formed when the universe was less than a second old, as it underwent a dramatic phase transition. Picture the universe cooling from an unimaginably hot, uniform state, like steam condensing into water droplets. As it cooled, the underlying fields that govern reality might have frozen into place in different configurations in different regions. Where these misaligned regions met, they could have trapped an immense concentration of energy into a line, a flaw in the cosmic structure. These lines would be cosmic strings, thinner than a proton but with the mass of a mountain range packed into every centimeter, stretching across the cosmos for light years. If they exist, they are not static. They would vibrate, whip, and sometimes snap under their own immense tension, and that is where the gravitational waves come in. A snapping cosmic string would not produce a smooth, sinusoidal wave. It would release a sudden, sharp burst of gravitational radiation, a distinct crackle in the detectors. This signal would be utterly unique, a fingerprint of the universe's infancy. Detecting such a crackle would be more than just discovering a new cosmic object. It would be a direct, experimental probe into the laws of physics at energy scales a trillion times higher than anything we can recreate in particle colliders. It would validate theories about the fundamental forces of nature and how they unified in the first instance after the Big Bang. We would be listening to the echoes of the universe's birth pangs, carried across time not by light, which was trapped, but by the pure vibrations of spacetime itself. The hunt for these phantom cracks is already on, a search for the scars left on reality as the cosmos took its first definitive shape. These cosmic crackles are whispers next to the universe's loudest possible shout. The merger of two supermassive black holes is the most energetic event that can occur since the Big Bang itself. To grasp this power, you must first abandon all earthly comparisons. A supernova, the explosion of a massive star, is blindingly brilliant, outshining its entire galaxy for weeks. Yet that is a mere spark against the inferno of a black hole collision. When two of these billion solar mass giants finally coalesce, the event unleashes a cataclysm that briefly outshines the combined light of every single star in the observable universe. Every galaxy, every quasar, every shining sun, all of them together are dimmed by this single violent act of creation. But here is the crucial, mind-bending detail: almost none of that energy comes out as light. It is released as pure, rippling gravitational energy. The peak luminosity in gravitational waves during the final moments of the merger is so immense it dwarfs the total electromagnetic output of the entire cosmos. For an instant, gravity itself becomes the brightest thing in existence. This flips our entire understanding of cosmic violence on its head. We are conditioned to think of the most powerful events as brilliant flashes, as things we can see. But in the realm of the most extreme gravity, sight is secondary. The true signature of the universe's ultimate cataclysms is not a flash in a telescope, but a tremor in the fabric of reality. It is a silent, dark storm of pure spacetime distortion, carrying away more power in a few seconds than all the stars will emit in their entire lifetimes. This is the hidden heart of the cosmos, where gravity, not light, writes the final chapter. That silent storm of gravity carries a hidden blueprint of the collision's final moments. When two black holes merge, the gravitational wave signal does not simply end with a crash. It enters a brief, crucial phase called the ringdown. Think of it like striking a bell. The initial impact is the violent merger, the loud clang, but what follows is the resonant ring, a pure tone that gradually fades as the bell settles. A newborn black hole rings in exactly the same way. After the chaotic collision, the single, distorted object vibrates wildly, shedding its asymmetries and settling into a smooth, symmetrical shape. These vibrations are not random noise. They produce gravitational waves at specific, pure frequencies, like the notes of a cosmic chord. This ringdown is the fingerprint of the black hole itself, encoding its final mass and, most importantly, its spin. By analyzing these fading tones, scientists can perform a direct test of one of the most fundamental predictions of Einstein's theory. General relativity dictates that a black hole's event horizon, the point of no return, must be perfectly smooth. It cannot have any bumps or hard surfaces. An exotic alternative, like a wormhole or a so-called gravistar, would have a different structure, a different kind of surface. And that difference would change the ringdown. A wormhole's throat might echo. A hard surface would reflect gravitational waves, producing a series of aftertones that a true black hole's event horizon would simply swallow without a trace. By listening intently to the ringdown signal and comparing its tones to the predictions of Einstein's equations, we are not just confirming a collision. We are conducting a forensic examination of the object that was created. We are asking the universe a direct question: is the event horizon truly the silent, smooth membrane we believe it to be, or does the signal carry the faint, telltale echoes of something even stranger lurking in the dark heart of gravity's victory? The ringdown of a black hole tests the fabric of reality, but there is a signal that could test the very origin of reality. Gravitational waves from the Big Bang itself may still be washing through the universe today. This is the ultimate extreme, a whisper from the first infinitesimal fraction of a second after creation. To understand this, we must go back before the first stars, before the first atoms, before even the first particles as we know them. Cosmologists believe the universe underwent a mind-bending growth spurt called inflation, an epoch where space itself expanded faster than the speed of light, smoothing and stretching the entire cosmos in less than a blink of an eye. This violent, exponential expansion did not happen in serene silence. The quantum foam of spacetime, a seething sea of uncertainty at the smallest scales, was stretched to cosmic proportions. Tiny quantum fluctuations, random jitters in the fabric of reality, were magnified into vast ripples across the universe. Some of these ripples became the seeds for all future structure, the slight overdensities that would one day collapse into galaxies and clusters of galaxies. But others took a different form. They became primordial gravitational waves, the first tremors in spacetime, generated not by colliding black holes, but by the birth pangs of the cosmos itself. These waves have been traveling ever since, a fossil imprint from the moment our universe truly began. Their detection would be the final, smoking gun proof for cosmic inflation and something even more profound. It would be our first direct observational link to the Planck epoch, a time when gravity and quantum mechanics were unified, at energy scales a trillion times beyond the reach of any particle accelerator on Earth. We would not be studying the universe's history, we would be touching its birth certificate. So how could we possibly hear such an ancient, faint murmur? The answer lies in the oldest light we can see. Those primordial gravitational waves, as they propagated through the early, hot, dense universe, left a unique signature on the cosmic microwave background, the afterglow of the Big Bang. They would have polarized this light in a very specific, swirling pattern known as B-mode polarization. It is a twist in the ancient light, a curl imprinted by the passing gravitational wave stretching spacetime one way and then the other. Finding this pattern is the holy grail of modern cosmology. It is a signal buried under 15 billion years of cosmic history and foreground interference, a whisper so faint that distinguishing it from the dust of our own galaxy is a monumental challenge. But the hunt is on, with telescopes at the South Pole and in space scanning the microwave sky with exquisite sensitivity. To detect this pattern would be to look directly into the furnace of creation, to witness the moment when the universe we know was forged from a quantum fluctuation, its first cry recorded not in light but in the permanent vibration of spacetime. The hunt for the universe's birth certificate is a search for the most ancient of whispers, but the gravitational waves we detect today have not traveled to us on a straight line through empty space. They too must navigate the cosmic landscape, and that journey can bend and warp them in extraordinary ways. Gravitational waves can be lensed just like light. This is a direct consequence of Einstein's theory. We know that a massive object like a galaxy or a cluster of galaxies warps the spacetime around it. When a beam of light from a distant star passes near this warped region, it does not travel in a straight line. It follows the curvature, bending around the massive object. From our perspective, that distant star's light appears to come from a slightly different position in the sky, or it can be magnified and even duplicated into multiple images like a cosmic mirage. This is gravitational lensing, and it has become a powerful tool for astronomers. Now apply that same principle not to light, but to the ripples in spacetime itself. A gravitational wave generated by a black hole merger in the distant universe travels outward. If its path to Earth takes it close to a massive galaxy cluster sitting halfway across the cosmos, the spacetime curvature of that cluster will act as a lens. It can bend the path of the gravitational wave. This bending can have several fascinating effects. It could magnify the signal, making a faint, distant chirp briefly louder and easier for our detectors to hear. More intriguingly, it could create multiple copies of the same event. Just as lensed light can produce multiple images of a single quasar, a lensed gravitational wave could arrive at our detectors 2 or even 3 times. We would hear the same cosmic crash, but each copy would have taken a slightly different path around the lensing object, arriving at a slightly different time. This echo effect would be a goldmine of information. By analyzing the time delays and the subtle distortions in each copy of the wave, scientists could perform a new kind of cosmic cartography. They could map the distribution of mass in the lensing galaxy cluster with unprecedented precision, including the mysterious dark matter that makes up most of its mass but emits no light. A lensed gravitational wave becomes a probe, not just of its violent source, but of every massive structure that lies between that source and us. It turns the entire cosmos into a complex lensing array, where the signals themselves are distorted by the hidden architecture of the universe, revealing the invisible scaffolding upon which galaxies are built. Lensing reveals the hidden architecture of the cosmos, but to hear its deepest, slowest rhythms we must construct a detector of staggering scale. The gravitational waves from orbiting supermassive black hole binaries are not just low in pitch, their wavelengths span light years. Our ground-based observatories, impressive as they are utterly deaf to this register. To tune into this cosmic bass, astronomers have engineered a detector that uses the galaxy itself. They call it a pulsar timing array, and it relies on the universe's most perfect natural clocks. Scattered across the Milky Way are millisecond pulsars, the rapidly spinning cores of dead stars. These objects are the remnants of supernova, compressed into spheres just a few kilometers across, yet containing more mass than our Sun. They spin hundreds of times per second, beaming out a lighthouse-like pulse of radio waves with a stability that rivals the best atomic clocks on Earth. Each pulse travels across the galaxy to our radio telescopes, arriving with metronomic regularity. This creates a galaxy-wide network of celestial timekeepers. The principle of detection is elegant in its simplicity. Imagine a vast, calm sea with a series of perfect buoys, each one bobbing up and down with absolute regularity. Now imagine a gentle, immense swell begins to pass through the entire sea. It doesn't break the surface violently, but it ever so slightly lifts every buoy, changing the rhythm of their bobbing in a correlated way. A low-frequency gravitational wave is that cosmic swell. As it passes through the galaxy, it minutely stretches the spacetime between us and some pulsars, while squeezing the spacetime between us and others. This stretching and squeezing changes the distance the radio pulses have to travel. For a pulsar in a direction being stretched, the pulses arrive a tiny fraction of a second later than expected. For one in a direction being squeezed, they arrive a tiny bit early. The key is that this pattern of delays and advances is not random. It follows a specific, correlated signature across the entire array of pulsars, a telltale fingerprint of a passing gravitational wave. The deviations are almost unbelievably small, measured in tens of nanoseconds over years of observation. It requires the patient, coordinated monitoring of dozens of these pulsars for a decade or more to separate this faint, universe-wide hum from the intrinsic noise of each cosmic clock. This is not astronomy of the instant, it is archaeology of space-time, sifting through layers of cosmic static to uncover the steady drumbeat of the universe's most massive objects dancing in the dark. Pulsar timing arrays listen for the slow hum of the universe, but the most extreme gravitational waves can also carry the secrets of matter itself. When two neutron stars spiral together in their final dance, the gravitational wave signal they produce becomes a detailed diagnostic tool, a cosmic ultrasound of unimaginable density. In the last few moments before collision, their immense gravity creates ferocious tidal forces. Each star stretches and deforms the other, pulling it into a teardrop shape as they whirl closer. This deformation is not just a dramatic visual, it is a crucial imprint left on the gravitational waves. The degree to which a neutron star stretches, its squishiness under this extreme pull, depends entirely on its internal composition. It is a property called tidal deformability, and it is encoded directly into the frequency and shape of the rising chirp we detect. Think of it like two identical-looking balls dropped from a height. One is a solid rubber ball, the other is filled with a thick, viscous fluid. They might look the same, but when they hit the ground, their behavior reveals what is inside. The rubber ball bounces sharply, while the fluid-filled ball splats with a dull thud. The gravitational wave from merging neutron stars is that moment of impact, and its precise sound tells us what the star is made of. This matters because the core of a neutron star is a realm of physics we cannot recreate. The pressure is so intense that atomic nuclei dissolve into a sea of neutrons and other particles, a state of matter so exotic it has no earthly analog. Theorists have proposed many possibilities for what form this matter takes. It could be a superfluid of neutrons, a crystalline lattice of exotic particles, or even a soup of free quarks, including the strange quark, creating a stable form of strange matter. Each of these theoretical states has a different stiffness. A star with a quark matter core would be much softer and more deformable than one with a rigid neutron crystal heart. By extracting the tidal deformability from the gravitational wave signal, scientists can effectively rule out entire categories of equations of state, narrowing down the possibilities for the true nature of matter at its absolute limit. The chirp from a neutron-star merger is not just a death knell, it is a direct message from the edge of physics, whispering the answer to a fundamental question: what happens to matter when you crush it beyond all recognition? The final mass of a newborn black hole is not a simple sum. When two black holes merge, the resulting object is almost always lighter than its parents combined. The missing mass is not lost, it is the price of the universe's loudest shout, converted entirely into the energy of the gravitational waves that announced the collision. For that first detected merger, the final black hole weighed in at 62 solar masses, a full 3 suns lighter than the initial 29 and 36 solar mass pair. That is 3 entire stars worth of mass transformed into pure spacetime vibration, a testament to the staggering efficiency of gravity's power plant. Yet sometimes the scales of cosmic justice tip in unexpected ways. The final mass can defy straightforward prediction, creating what scientists might call overweight or underweight offspring. This puzzling outcome hinges on a subtle but powerful factor: the spin of the original black holes. Think of 2 figure skaters in a final, gripping embrace. If they are spinning rapidly in the same direction as their orbit, their motion adds a kind of rotational energy to the system. This extra energy acts like a booster, allowing them to orbit closer together before the final plunge. More of their mass is converted into gravitational waves in that last, furious instant. The result is a final black hole that is surprisingly light for its pedigree, an underweight champion. Conversely, if one or both black holes are spinning against the direction of the orbit, it is like trying to clasp hands while spinning in opposite directions. The system is less efficient, more chaotic. They cannot get as close before merging, so less mass is radiated away. The final product retains more of the original mass, becoming an unexpectedly heavy offspring. These spin dynamics are not just a minor detail, they are a fundamental challenge. By measuring the final mass and comparing it to the gravitational wave signal, scientists can infer the spins of the original black holes, revealing their history. Were they born from stars that collapsed together, spinning in alignment, or were they brought together later in a chaotic galactic dance with spins wildly askew? Each merger is a unique experiment, and the weight of its dark child tells a story about the violent, spinning dance that created it. The weight of a newborn black hole tells a story of spin and energy, but the gravitational wave signal itself carries a far more precise piece of information, one that could recalibrate our entire map of the cosmos. These waves are not just messengers of violence, they are a revolutionary new kind of cosmic ruler. The amplitude of a gravitational wave, its loudness as it reaches our detectors, holds a direct and simple secret. It tells us exactly how far away the source is. This transforms each black hole or neutron star merger into what cosmologists call a standard siren. Think of it like this: if you hear a foghorn, the volume tells you roughly how close the ship is. A very loud horn is likely nearby, a faint one is far away. But with fog, you cannot see the ship to confirm its distance. In traditional astronomy, we face a similar challenge. We measure cosmic distances using a complex, interlinked chain of methods called the cosmic distance ladder. We start with parallax to nearby stars, use those to calibrate certain types of variable stars in farther galaxies, and then use those galaxies to calibrate even brighter supernovae. Each rung on this ladder depends on the one below it, and tiny uncertainties can accumulate over billions of light years, leading to a growing margin of error. A gravitational wave standard siren cuts through that entire fragile structure. The physics is beautifully direct. We can analyze the waveform to know the intrinsic strength of the event, the true loudness of the horn at its source. By comparing that to the faint amplitude we actually measure, the volume at our detectors, we can calculate the distance with no ladder required. It is a one-step measurement, a pure geometric test of the universe's scale. This is why the detection of the neutron star merger GW170817 was a landmark. We had the gravitational wave giving us a direct distance to the source. And we had telescopes pinpointing its host galaxy, providing a traditional redshift-based distance. For the first time, we could cross-check 2 completely independent cosmic measuring tapes. This new tool is now being used to tackle one of the biggest puzzles in modern cosmology, the Hubble tension. Different methods for measuring how fast the universe is expanding are yielding stubbornly different answers. It is as if 2 meticulously crafted clocks built to the same blueprint are ticking at different rates. Standard sirens offer a third, pristine clock. By collecting a population of these events at different distances, We can measure the expansion rate of the universe, the Hubble constant, in a way that bypasses all the old assumptions and potential pitfalls of the cosmic distance ladder. Each chirp from the dark is more than a story of collision. It is a precise beacon, a single point of light on a new, independent map of an expanding universe, helping us resolve which of our cosmic clocks is telling the true time. The standard siren gives us a cosmic ruler, but the extreme warping of gravity can twist that ruler into a knot so profound it challenges our very understanding of cause and effect. Some of the most exotic mathematical solutions to Einstein's equations suggest that a sufficiently intense, rotating gravitational wave could theoretically create a closed time-like curve. This is not science fiction, but a stark mathematical possibility arising from the raw power of warped spacetime. Picture a path through the universe, not through space, but through time itself. In our normal experience, time is a one-way street, an arrow pointing relentlessly from past to future. You cannot revisit yesterday any more than you can unscramble an egg. But within the ferocious whirlpool of spacetime generated by something like a pair of rapidly spinning, merging black holes, the equations of general relativity allow for a path that loops back on itself. A closed time-like curve would be a corridor in spacetime where you could travel forward in time along a route that eventually brings you back to your own past, a cosmic Möbius strip of causality. It is the ultimate expression of gravitational waves, not just bending space, but tying time into a pretzel. The key ingredient is rotation. A non-spinning gravitational wave simply stretches and squeezes. But a powerful, rotating wave, like that from black holes with immense aligned spins, adds a twisting motion to the fabric of reality. This twist could, under mathematically perfect and extreme conditions, become so severe that the future direction on your timeline smoothly connects back to a point in your own past. You would not need a machine. You would simply follow the distorted geometry of the universe itself, walking a path laid down by the most violent events in existence. Of course, most physicists believe such paradoxes are physically impossible. The consensus is that quantum effects, the laws of the very small, would conspire to prevent a closed time-like curve from ever forming in reality. Something called the chronology protection conjecture suggests nature abhors a time-travel paradox as much as it abhors a vacuum, and would intervene, perhaps through a buildup of infinite energy, to snap the loop before it could be used. Yet the mere theoretical possibility is a breathtaking reminder. The gravitational waves we are now detecting are not just signals. They are proof that the universe can warp time itself to degrees that flirt with the logically impossible. Each chirp we hear is a snapshot of a realm where time is not a rigid backdrop, but a flexible, malleable substance stretched, twisted, and shaken by the dark giants of the cosmos. The theoretical knots of time travel are a stark reminder of the raw power we are measuring. But our detectors are not just listening for these mathematical extremes, they are conducting a vast, ongoing census of the dark universe. Since that first historic chirp, the LIGO and Virgo observatories have heard dozens of mergers, transforming gravitational wave astronomy from a miraculous first hearing into a routine form of observation. Each detection is a data point, and together they are sketching a population map of the universe's most elusive objects. We are no longer waiting for a single, rare event. We are now statistically analyzing the lives and deaths of black holes and neutron stars across cosmic history. This new census is revealing startling truths. Before these detections, we had only indirect evidence for stellar mass black holes, mostly from a handful of X-ray binary systems in our own galaxy. The gravitational wave catalog has exploded that sample size. We now know of black holes merging with masses far heavier than any we had seen before, some in the so-called upper mass gap where theory suggested they should not easily form. We are discovering that black holes of 20, 30, even 50 solar masses are not rare anomalies, but common products of stellar evolution in certain environments. The data is also telling us how often these catastrophic dances occur. Current estimates suggest a stellar mass black hole merger happens somewhere in the observable universe roughly once every few minutes. Our detectors are simply catching the loudest, closest ones. This rate is a crucial number. It tells astrophysicists if their models for how massive stars live, die, and find partners are correct. Every new chirp added to the catalog refines the picture, revealing the preferred mass ranges for these dark objects and hinting at the different pathways that lead them to collide. Are they born together in tight binary star systems, or are they thrown together later in the dense cores of star clusters? The statistics of their spins and masses hold the answer. This is the power of moving from a single snapshot to a full photo album of cosmic violence, allowing us to see not just the individual events, but the broader story of how the universe recycles matter into darkness and rings spacetime with the echoes of endless stellar demise. That statistical census of the dark universe is written in a language we can now translate into sound. The raw data from LIGO and Virgo is a squiggle on a graph, a precise but silent mathematical curve. Scientists, however, have found a way to let us listen in directly through a process called sonification. They take the gravitational wave signal and shift its frequency into the range of human hearing. What was an inaudible ripple in spacetime becomes a sound you can play on your speakers, and each type of cosmic catastrophe has its own distinct voice. The merger of two black holes produces that now iconic chirp. You hear a rapid, sweeping rise in pitch, from a low rumble to a high-frequency climax in a fraction of a second, followed by a quick ring down. It is the sound of the final, frantic orbits before the two objects become one. A neutron-star collision tells a different story. The signal is longer, sometimes lasting for minutes, and it has a different texture. The rising tone is often compared to the sound of a bird's chirp, but it can end not with a clean ring, but with a softer thud or a messy crunch, reflecting the complex, shattering explosion of dense matter. Then there are the theoretical possibilities, like the snap of a cosmic string. That signal would not be a smooth tone, but a sharp, sudden crackle, like static discharge or the snap of a whip. A burst of noise representing a one-dimensional flaw in reality itself snapping under its own immense tension. This act of sonification is more than a neat trick. It makes an abstract mathematical phenomenon viscerally real. It allows us to experience the data with a different sense, to feel the acceleration, the violence, and the finality of these events in a profoundly human way. You are not just looking at a graph, you are hearing the fabric of the universe itself ring like a bell, tear like cloth, or crack like ice. It turns the cosmos from a silent movie into a gripping radio drama, where every chirp, thud, and crackle is a chapter in the epic of gravity's dominion. The symphony we hear today is only the opening movement. Our current detectors are like listening to a grand orchestra through a keyhole, catching only the loudest, highest-pitched instruments. The future promises to swing the doors wide open. A new generation of observatories is on the drawing board, each designed to listen to a different part of the gravitational wave spectrum, transforming our whisper of the cosmos into a full, resonant chorus. Leading this charge is the Laser Interferometer Space Antenna, or LISA, a mission that will launch 3 spacecraft into orbit around the Sun. Flying in a perfect triangle with arms 2.5 million kilometers long, LISA will be tuned to the low-frequency hum that ground-based detectors cannot hear. It will listen for the stately, million-year waltz of supermassive black hole binaries as they spiral together in the hearts of distant galaxies. It could hear the gentle chirp as a small black hole gets captured by a supermassive one, tracing intricate patterns in spacetime for years before the final plunge. LISA will open the bass register of the universe, revealing the slow, deep rhythms that govern the largest structures in existence, but the ambition does not stop in space. On Earth, plans are underway for colossal successors to LIGO. The Einstein telescope in Europe and Cosmic Explorer in the United States envisioned detectors with arm lengths of 10 kilometers or more, built with revolutionary seismic isolation and cryogenic cooling to silence even the quantum noise of atoms. Their sensitivity will be breathtaking. They will hear the merger of two neutron stars anywhere in the observable universe, turning rare events into a routine daily occurrence. They will listen so deeply into the cosmos that they could detect the very first black holes to form after the Big Bang, the primordial seeds from which all later structure grew. Together, this network of cosmic listeners will create a complete gravitational wave observatory. From the high-pitched chirp of the first stellar deaths to the low thrum of every supermassive pair in the cosmos, we will have a continuous, evolving soundtrack of the universe's history. We will move from detecting individual crashes to monitoring the entire gravitational ecosystem, watching the universe evolve not through light, but through the vibration of its very fabric. Every single gravitational wave detection is a direct, brutal test of Einstein's century-old theory. As two black holes spiral and merge in a region of space-time bent beyond all earthly recognition, they are performing the ultimate experiment in strong field gravity. The exquisite data from LIGO and Virgo allows scientists to compare the precise shape of the detected wave to the detailed predictions of general relativity. The result so far is a staggering confirmation. The waves match Einstein's equations with incredible precision, even in these regimes of unimaginable curvature where gravity is billions of times stronger than anything in our solar system. It is as if we built a bridge based on a mathematical formula and then drove the heaviest truck in the world across it, only to watch the bridge hold perfectly without a single tremor. This repeated success under such extreme duress is a monumental triumph for the theory. Yet, physicists are almost eager for it to fail. The quiet hope is that a future detection, perhaps from an event of even more staggering violence, will show a tiny, persistent deviation. A slight mismatch in the ring-down frequencies or an unexpected wobble in the in-spiral phase. Why would a flaw be so exciting? Because general relativity, for all its beauty, is a classical theory. It describes gravity as the curvature of smooth space-time, but we know the universe is fundamentally quantum at the smallest scales. There must be a deeper theory, a quantum theory of gravity, that merges Einstein's cosmos with the strange rules of particles and forces. The most likely place to find hints of this new physics is where gravity becomes both incredibly strong and operates on the scale of the very small, like at the very edge of a black hole's singularity or in the first instant after the Big Bang. A gravitational wave from an event that pushes these boundaries could carry the faint fingerprints of quantum gravity, a subtle crack in the classical facade. Each new chirp from the dark is therefore more than data, it is a potential revolution. It could either further cement Einstein's legacy in stone, or it could provide the first clue that leads us to the next great theory of everything, written in the language of spacetime's own vibrations. The search for quantum echoes in gravitational waves points toward a deeper cosmic unknown. Our entire map of the universe tells us that the matter we see, the stars and galaxies and planets, is only a tiny fraction of what actually exists. The rest is dark matter, an invisible substance that holds galaxies together and shapes the cosmos, yet has eluded every direct search for decades. Gravitational waves may offer a radical new path to find it. One compelling hypothesis suggests dark matter could be made of ancient, primordial black holes. These would not be the black holes formed from dying stars, but ones forged in the extreme density of the universe's first second, spanning a vast range of sizes from an asteroid's mass to many times that of our Sun. If these primordial black holes drift through the cosmos as dark matter, then occasionally two of them should find each other and merge. That collision would send out a gravitational wave chirp, but one with a very distinctive signature. A merger between two asteroid-mass black holes would produce a signal far higher in frequency than anything LIGO can detect, a sharp, almost ultrasonic ping. Future, more sensitive instruments might hear a faint chorus of these pings from the dark matter halo of our own galaxy, a direct announcement that the missing mass of the universe is actually a swarm of ancient black holes. But there is another, even more exotic possibility. Dark matter might be composed of theoretical particles like actions, incredibly light particles that could form vast diffuse clouds. In the intense gravity near a spinning black hole, a billion solar mass cloud of actions could condense, forming a ghostly atmosphere around the darkness. This cloud would not be static. It would interact with the black hole's spin, creating a continuous, monochromatic hum of gravitational waves. Unlike the transient chirp of a collision, this would be a steady, pure tone, a single note ringing across the cosmos from the heart of every galaxy with a suitable black hole. Detecting this persistent whisper would be a twofold revelation. It would confirm the existence of actions, solving a major puzzle in particle physics, and it would simultaneously identify the nature of dark matter itself. We would learn that the invisible scaffold of the cosmos is not made of dead stars or unknown particles streaming through our labs, but of ghostly quantum clouds singing in the dark, their faint song carried to us on ripples in spacetime. That ghostly song of dark matter is a whisper compared to the detailed story told by a single gravitational wave chirp. A signal from a black hole merger is not a simple blip. It is a dense, information-rich fingerprint, a cosmic data stream encoded in the precise shape of its rising tone and final ring. Physicists can listen to this single sound and extract an astonishingly complete biography of the colliding objects. They can calculate the final mass, yes, but they can also reverse engineer the individual masses of the two original black holes, their immense spins, and even the precise orientation of their orbit. Each of these parameters leaves a distinct mark on the gravitational waveform. The masses determine the overall frequency and duration of the chirp. Heavier black holes produce a lower-pitched, shorter signal, while lighter ones create a higher, more drawn-out tone. But the spins add a layer of complexity. A rapidly spinning black hole drags spacetime around with it, an effect called frame dragging. When two spinning black holes orbit each other, this dragging subtly modifies their dance, changing the rate at which they spiral inward. That change is imprinted on the gravitational wave signal as a specific distortion in the waveform's shape. By fitting the observed signal to millions of theoretical templates, scientists can deduce not just if the black holes were spinning, but the direction and magnitude of each spin. Were they spinning in the same direction as their orbit, like two tops spinning smoothly together on a table? Or were they wildly misaligned, tumbling chaotically as they fell toward each other? This spin data is a direct clue to the binary's origin story. A pair of black holes born together from a binary star system will likely have spins aligned with their orbit, a legacy of their shared birth cloud. But if two black holes were thrown together later in life, captured by each other's gravity in the crowded core of a globular star cluster, their spins would be randomly oriented, a telltale sign of a chaotic courtship. The orbit's orientation adds another clue. The gravitational wave signal is slightly stronger if we view the merger face-on, looking down at the orbital plane, and slightly weaker if we see it edge-on. The precise amplitude of the signal we measure reveals our viewing angle. All of this information, masses, spins, orbit, is woven together into that single, fleeting ripple. It is a forensic audio recording of a catastrophic event, allowing us to reconstruct not just the final collision, but the entire life history of two dark giants, from their violent births to their even more violent end. That forensic audio recording reveals the final, brutal truth of Einstein's universe. Gravitational waves are not a rare cosmic anomaly or an exotic byproduct of only the most extreme events. They are the inevitable, universal consequence of a cosmos in motion. Any mass that accelerates, that changes its speed or direction, will generate these ripples in spacetime. Our Earth orbiting the Sun does it. Your hand waving through the air does it. Every star, every planet, every galaxy moving through the void is constantly broadcasting its own faint gravitational whisper into the darkness. The signal from a black hole merger is simply that same physics amplified to a universe-shaking scream. Their detection does more than reveal hidden objects. It confirms the fundamental nature of reality itself. Spacetime is not a rigid, unchanging stage upon which the drama of matter plays out. It is a dynamic, flexible fabric, an active participant in the cosmic story. Matter tells spacetime how to curve, and curved spacetime tells matter how to move. This beautiful, endless dialogue creates vibrations, the gravitational waves that carry news of every acceleration across the light years. We are now, for the first time, tuning into that conversation. Every chirp we hear is a direct link, a thread of vibrating spacetime connecting our quiet corner of the universe to the most violent transformations happening anywhere at any time. It means we are no longer isolated observers of a silent cosmos. We are embedded within a living, breathing, ringing universe, one that vibrates with the motion of all things, from the gentle dance of planets to the final, dark embrace of colliding giants. This revolution in how we perceive the cosmos is only just beginning. For all of human history, we have been astronomers of the light, our eyes and telescopes bound to the electromagnetic spectrum. But the universe is not silent. It thrums with the motion of matter, a vibration in the very stage upon which the cosmic drama unfolds. The 25 facts we have explored are not isolated curiosities. They are chapters in a new story, one written in the language of spacetime itself. From the first chirp of colliding black holes to the theoretical crackle of cosmic strings, gravitational waves have handed us a new set of senses. We can now hear the gold being forged in neutron star kilonovas, map the distribution of dark matter through lensed echoes, and even listen for the birth pangs of the Big Bang in the polarization of ancient light. This is more than a new tool, it is a fundamental shift. We are no longer watching the silent movie of the cosmos. We are experiencing it in full, immersive sound, hearing the hidden violence that light could never reveal. Each detection is a direct probe into the heart of gravity, testing Einstein's equations in the most extreme regimes and searching for the faint whispers of quantum physics. It allows us to witness the formation of the first black holes, measure the expansion of the universe with pristine rulers, and census a dark population of objects we never knew existed. The promise is that the next signal, the next ripple to wash over our planet, could be the one that changes everything. It might carry the ring of a wormhole, the hum of an action cloud solving dark matter, or the primordial swell that finally tells us how our universe began. This new window is open and the symphony is playing. All we have to do is keep listening. If you want to be there for the next great discovery, to dive deeper into the mysteries of black holes, dark energy, and the fabric of reality, make sure you are subscribed. The universe has so much more to tell us, and the conversation has only just begun.